Chapter 1.4.2.1 Deployments. A deployment in Kubernetes is used to make declarative updates to pods and replica sets by defining a desired state. The deployment controller then works to change the actual state to match the desired state at a controlled rate. Deployments can be used to create new replica sets or remove existing ones and adopt their resources with new deployments. It is important not to manage replica sets owned by a deployment. If your specific use case is not covered in the documentation, it is recommended to submit an issue to the main Kubernetes repository for assistance. Use case. Typical use cases for deployments include creating a deployment to roll out a replica set, checking the status of the rollout, declaring the new state of pods, creating a new replica set and managing pod migration, updating deployment revision, rolling back to earlier revisions, scaling up deployment for more load, pausing and resuming rollouts, using deployment status as an indicator of rollout progression, and cleaning up older unnecessary replica sets. These processes help in managing and maintaining the state of pods in a controlled and efficient manner. Creating a deployment. A deployment named Nginx deployment is created in the example provided, which involves creating a replica set to bring up 3 Nginx pods. The deployment specifies the name, replicas, and selector for the pods to manage. The pod template includes labels to define the type of application running, app Nginx, and the container specifications for running the Nginx Docker image. To create the deployment, you need to ensure your Kubernetes cluster is up and running and follow the steps mentioned in the text. Running specific commands such as kubectl get deployments allows you to check the status of the deployment, including the number of replicas available, up to date, and running. You can also check the status of the rollout and view the replica set created by the deployment. The replica set generated by the deployment ensures that there are 3 reliable Nginx pods running. It is essential to use appropriate selectors and labels in a deployment to avoid conflicts with other controllers. The pod template hash label is automatically added by the deployment controller to prevent overlapping selectors and ensure the proper functioning of the pods. Changing this label is not recommended, as it could lead to unexpected behavior in the Kubernetes cluster. Overall, the text provides a detailed example of deploying Nginx pods using a deployment in Kubernetes. It covers the necessary steps to create and monitor the deployment, manage replicas using a replica set, and ensure proper labeling to avoid conflicts with other controllers. The cautionary note regarding the pod template hash label emphasizes the importance of maintaining consistency and avoiding overlap to maintain the stability of the deployed application. Updating a deployment. The text discusses the process of updating a deployment in Kubernetes, specifically focusing on triggering rollouts when changes are made to the deployment's pod template. It outlines steps to update a deployment to use a new image, such as changing the container image from Nginx 1.44.2 to 1.60.1. The text also explains how to view the rollout status and details of the updated deployment using kubectl commands. It further delves into how deployments ensure that only a certain number of pods are down while being updated, with default settings ensuring at least 75% of the desired number of pods are up, and at most 125% are created above the desired number. The text provides insights into how deployments manage the creation and deletion of pods during updates, ensuring availability of pods within specified limits. The text also discusses the concept of rollover or multiple updates in flight, explaining how existing replica sets are scaled down and new ones are created as deployments are updated. It details the process of rolling over replica sets and scaling them up or down based on the update. It also highlights the need for caution when performing label selector updates, as they can result in orphaned replica sets and the creation of new ones. Overall, the text provides a comprehensive guide on how to update deployments in Kubernetes, including best practices, default settings, and considerations for label selector updates. It emphasizes the importance of understanding the implications of changes made to deployments to ensure smooth and efficient updates. Rolling back a deployment. When managing deployments in Kubernetes, it is important to be able to roll back to previous stable versions in case of issues such as crash looping. The system keeps a history of all deployment revisions, which are created when changes are made to the deployment's pod template, such as updating labels or container images. Scaling the deployment does not create a new revision, allowing for simultaneous manual or auto-scaling. If a mistake is made during an update, such as a typo in the container image name, it can cause the rollout to get stuck. In this case, checking the rollout status and roll back to a stable revision is necessary. To roll back to a previous version, the revision history of the deployment can be checked, and specific revisions can be rolled back to. Rolling back to a previous revision can be done using the Kubernetes CLI with commands such as kubectl rollout. This will generate a deployment rollback event, indicating that the deployment has been successfully rolled back to a stable version. It is important to verify that the rollback was successful and that the deployment is running as expected. Overall, being able to roll back deployments in Kubernetes is a crucial aspect of managing deployments and ensuring system stability, especially in cases of errors or instability. By following the appropriate steps and commands, deployments can be efficiently rolled back to previous stable versions. Scaling a deployment. Scaling a deployment in Kubernetes involves setting up an autoscaler based on CPU utilization and specifying the minimum and maximum number of pods to run. Rolling update deployments allow multiple versions of an application to run simultaneously, and proportional scaling is used to balance additional replicas during a rollout. In a scenario where a new image update is blocked due to a max unavailable requirement, a new scaling request prompts the autoscaler to increment deployment replicas and distribute them across existing replica sets based on a proportional scaling strategy. This ensures that additional replicas are spread across all replica sets, with bigger proportions going to replica sets with more replicas and leftovers added to the replica set with the most replicas. The rollout process should eventually move all replicas to the new replica set, as confirmed by checking the rollout status. This process helps maintain stability and mitigate risks during scaling operations in Kubernetes deployments. Pausing and resuming a rollout of a deployment. When updating a deployment, you have the option to pause rollouts before triggering updates, allowing you to apply multiple fixes without unnecessary rollouts. This process involves getting deployment details, checking rollout status, and pausing the rollout using commands. You can update the image or resources of the deployment while it is paused, ensuring that new updates will not take effect until the rollout is resumed. Once you resume the rollout, a new replica set with all the updates will be created, and you can monitor the status until it is completed. It is important to note that a paused deployment cannot be rolled back until it is resumed. This method ensures that updates can be made efficiently and effectively without disrupting the deployment's functionality. Deployment status. A deployment in Kubernetes goes through different states during its lifecycle. It can be progressing, complete, or fail to progress. A deployment is marked as progressing when it creates a new replica set, scales up or down its newest replica set, or when new pods become ready. The rollout is considered complete when all replicas associated with the deployment have been updated to the latest version, all replicas are available, and no old replicas are running. A failed deployment can occur due to various factors such as insufficient quota, readiness probe failures, or application misconfigurations. To detect a stalled deployment, a progress deadline can be set in the deployment spec. Once the deadline is exceeded, the status will show a progress deadline exceeded condition, and the deployment can be rolled back to its previous version by higher-level orchestrators. Pausing a deployment does not trigger the deadline condition. Transient errors can also occur, such as insufficient quota, which can be addressed by scaling down the deployment or increasing quota in the namespace. A successful deployment will have a status of true and a reason of new replica set available for the available condition, indicating minimum availability. For a progressing deployment, a status of true and a reason of new replica set available means the deployment is complete. You can check if a deployment has failed to progress by using kubectl rollout status, which will return a non-zero exit code if the progression deadline has been exceeded. Actions that apply to a complete deployment, such as scaling, rolling back, or pausing, also apply to a failed deployment. Cleanup policy. The text explains how the .spec.revision history limit field in a deployment can be used to determine how many old replica sets are retained. By default, this value is set to 10. If the field is set to 0, all history will be cleaned up, preventing the deployment from being able to roll back. This setting allows for controlling the retention of old replica sets in a deployment. Canary deployment. To roll out releases to a subset of users or servers using deployment, create multiple deployments for each release following the canary pattern described in Managing Resources. This allows for testing before full deployment. Writing a deployment spec. A deployment in Kubernetes requires specific fields such as API version, kind, and .metadata. The metadata.name of a deployment is used as the basis for naming new pods created by the control plane and must be a valid DNS subdomain value. The .spec section of a deployment includes the .spec.template and .spec.selector, which are required fields. The .spec.template is a pod template that must have appropriate labels and a restart policy. Spec.replicas specifies the desired number of pods, with the default being 1, and can be manually scaled or managed automatically by the control plane. The .spec selector must match .spec template metadata.labels and is immutable after creation in apps v1. The .spec strategy field specifies whether the deployment will use a recreate or rolling update strategy. With a recreate strategy, all existing pods are killed before new ones are created, while a rolling update strategy updates pods in a rolling fashion. The rolling update process can be controlled with the max unavailable and max surge fields. A deployment can also have a progress deadline seconds field to specify how long to wait for progress before declaring a failed progressing condition. The revision history of a deployment is stored in the replica sets it controls, and the revision history limit field specifies how many old replica sets to retain for rollback purposes. Setting this field to 0 means that all old replica sets with 0 replicas will be cleaned up, making it impossible to undo a new deployment rollout. The spec.paused field allows pausing and resuming a deployment, preventing new rollouts when changes are made to the pod template spec. Overall, a deployment in Kubernetes is a complex entity that requires careful configuration and management to ensure the successful deployment and scaling of applications. By understanding and correctly setting the various fields and strategies available, developers can effectively control the behavior and life cycle of their pods within a Kubernetes cluster.